Hello, in this video I'm going to run through a couple of outstanding topics that I haven't fitted into the previous videos on forces and dynamics. So that's drag and terminal velocity, which is one of the topics. They sort of get associated together. And then the other topic is upthrust and buoyancy. So let's start with drag and how that leads on to terminal velocity. So drag is something that occurs when you've got movement through a fluid. You'll see this in textbooks quite a lot. They talk about movement through a fluid. That doesn't necessarily mean a liquid. So gases can be treated as a fluid as well, certainly in the case of drag. So we're looking resistance to motion is what we're looking at here. So if you've got air resistance, or if you've got something moving through water or some other liquid, then you're going to have resistance to motion because you're having to push through this material. You're pushing through a fluid. So it's like, as I say, it's a resistive force. It's something that we're classifying in the same group as friction and things like that. It's something which is opposing the motion. And drag increases with speed. This is the main thing that we see. We don't have a simple formula that we use for working out drag. There will be things that are given to us in an exam question or some other problem that we need to solve. It's not something that's written in a formula booklet, but something that comes up time and time again is that the drag is proportional to the square of the speed. This is a common finding in experimental physics, that people have empirically found this out, but there's so much complexity about what drag force you're going to get, because it's not just dependent on the speed, it's dependent on the surface area of the object, the density of the fluid, the roughness of the surface of the object. There's so many factors that get built into it that we can't just say, okay, here is some formula of drag equals something. It's something that needs to be empirically determined based on a particular situation. So that's why they're always going to provide us with some relationship or formula in the question or problem that we're trying to solve. In the real world, if we're trying to quantify drag, then you have to start doing a lot of experimental work. This is why they have things like wind tunnels and things like that. You can start quantifying things then, looking at the flow of the object through the fluid, or in the case of a wind tunnel, the fluid over the object, and then start turning that into some description specific to that object and the fluid. But drag does lead to terminal velocity. So if you've got some object, say you've got something is dropped into water, this object is now falling through the water. You've got the weight acting downwards. You've got the drag acting upwards. Now the resistive force, we're not going to get a greater resistive force than we are of the driving force. So this drag is never going to exceed the weight. It's like we have with friction. You're not going to suddenly get more friction than you need in this. We start off that we're moving at some speed downwards, and the drag is going to be proportional to the square of that speed. If we've still got a resultant downward force because the weight is greater than the drag, well, we've then got an acceleration. That means we've got an acceleration going downwards, which means the speed is going to increase. So the speed goes up, which means that the drag will go up. And eventually the drag will keep on increasing until it's equal to the weight. When the weight and the drag are equal to each other, we've then got no acceleration. We've reached this equilibrium, and then according to Newton's first law, of course, we've got no net force acting on the object. It's just going to continue at this same velocity. This is the terminal velocity. Something that sometimes people get confused with this is the idea that we've got they think, oh yeah, we've got an upwards acceleration. Well, we don't have an upwards acceleration. the acceleration is always downwards or zero. And this acceleration downwards in this particular scenario is just decreasing until eventually it reaches zero. So we are tending towards this maximum velocity. If we were going to draw a velocity time graph, then it's going to be, something which is doing this. It's tending towards this terminal velocity. But the gradient, which of course is the acceleration, is decreasing all the time until eventually it's zero. So we've got this decreasing gradient, this decreasing acceleration. If we're going to start getting an upwards force, a net upwards force, we can't get that just from drag. This is where, as we're going to see in a moment, this is where we need to start looking at the buoyancy of the object, because it's going to be upthrust which is giving the upwards force. It's not the drag. So yeah, that's what's going on with drag and terminal velocity, is resistance to motion when an object is moving through a fluid, and that can increase up to the driving force, which in most of the questions that we end up looking at, the driving force is the weight of an object, because we've either got something falling through liquid, as we've just had in this case, or we might have, the skydiver, he opens his parachute, and now we've got his weight is driving his motion downwards, and we've got the drag which is slowing it down. So yes, so that's what's going on with our drag. So let's start thinking about buoyancy then, and upthrust. Well, let's start with the two words themselves. So buoyancy is a description of an object's tendency to float in a liquid. Is it going to float? Is it going to sink? Is it just going to sort of hang around where it is? If something is buoyant, it's got greater tendency to float. So usually it's lower density. Now this will depend upon the liquid that it's in, as we'll see later on. Some things will float in some liquids and not in others. So that's our descriptive term. Upthrust is more of I suppose a technical physics term. This is the actual force which is causing the object to float. It's or to slow down its descent. This is the upwards acting force on an object. So this is different to the drag. The drag is coming from resistance to the motion. The upthrust is a force produced by an object's position inside a liquid. So we need to distinguish these two things as different, the difference between the drag and the upthrust. So if you've got an object that's held in place in a liquid, so it's not moving at all, it's in a liquid, it's not moving, it's just being held there. Maybe you've got your finger just sitting on top of it and you're holding it in place. It will have no drag because it's not moving, but it will have upthrust because it is located inside the liquid. So they're separate things. And sitting behind all of this, we've got Pascal's law, which gets often overlooked when we get to A level. I don't know why. I think it comes up at GCSE and other pre-16 physics classes. So we got Pascal's law. So this is this is how force is transmitted through a liquid. So if you've got some, a good way to think about this is when you've got pistons and things like that. So you get these setups where you've got some little piston over here which you're pushing down, or even on the other side. So you've got a pair of them. It doesn't really matter which way you're doing this. You've got two of these and they're connected here. This is all liquid. You might have water in here. You've got some hydraulic system going on. And if you've got, so there's two things we need about this system. We need an enclosed and an incompressible system. We need an enclosed and an incompressible fluid. So now with fluids, we said before, fluids can apply to gases or liquids, But if we're going to have an incompressible one, well, we're not going with gases here. I mean, you can have compressed air and things like this, but really for these systems, we want something like water that you can't really compress, or not very much anyway. So we've got an enclosed and an incompressible fluid. It's not leaking out anywhere. We can't squish it anywhere. So that's the first thing. If you apply a force to one part of this fluid, because obviously the fluid's all connected everywhere, you push down on one end here with a certain force. Okay, that's going to create a pressure inside the liquid, because we've got a force divided by the area. So this is creating pressure. For an enclosed and incompressible fluid, that pressure is transmitted equally and undiminished throughout the liquid to all points in all directions. So that pressure that is felt here will be felt by every single point throughout the liquid. So we've got this transfer of force, this transfer of pressure throughout the liquid. And that's to underlying what's going on with the calculations when we start looking at buoyancy. So if we're going to start looking here at the pressure from a column of liquid, you've got some amount of liquid. We take a column of this, let's say it's a cylindrical column of liquid, and we can say it's of height h and it's got area A. Then we know that we've got the weight acting downwards. This weight is equal to the mass of that cylinder multiplied by g. The mass is the density times the volume, and then we can say the volume is h times a. So we've got rho h a g. We've got, this is our force downwards at the bottom of this column of liquid. So if we now want to turn this into a pressure, the pressure at the bottom is the force divided by the area. So the pressure at the bottom of this cylinder is going to be rho times h times g. So we've now got a description of the pressure at the bottom, and that pressure here is transmitted throughout the liquid. So we've got that pushing downwards, we've got the same thing pushing upwards, which of course is just going to be keeping the liquid at the bottom of the cylinder in equilibrium, because we've got this pressure acting in both directions. But this pressure is transmitted everywhere, and you've got different pressure at every depth, but it's pushing in all directions. So, and that is really important when you then put an object inside the liquid, because all surfaces of the object are going to be pushed with the pressure at that depth. So all surfaces are going to be getting pushed. So the top is going to get pushed down, the bottom is going to get pushed up, and each one of the sides are going to get pushed. The right hand side will get pushed to the left hand side will get pushed to the right. So for horizontal motion, because they're at the same depth, they've got the same pressure, so they've got the same force, so they're going to be cancelling out. So these are going to cancel out with each other. But looking at the difference between the top and the bottom, the top's being pushed down and the bottom's being pushed up, but we got greater pressure at the bottom than we have at the top. So this arrow going upwards is a greater force than the arrow going downwards. So we've got a net upwards force, and that is the upthrust. When it's just sitting there, so if we're going to hold an object in place, an object that would normally float, then we're going to we have to provide that extra force downwards to stop the thing popping up to the surface. You have to hold a cork under the water to stop it floating. So how do we quantify then this upthrust? So we know it's the difference between these pressures. Well, if we've got a difference in depth, say let's get rid of these x's, which we're cancelling out, and say our difference in depth, like the thickness of this object is x, then at the top we've got a force downwards. So let's take our pressure multiplied by the area again. So say the area is A, then we can say we've got H times A times rho times G. At the bottom, we've now got H plus X times A times rho times G. And we need the difference of those is going to be our net force. So that's just going to leave us that the difference in the force between top and bottom is X times A times rho times G. So remember here, this is the density of the liquid. That is the density of the liquid, not of the object. Remember we got that here. That density there, that's the density of the liquid. So we can then see that this bit here, this is the volume of the object multiplied by the density. So that is the mass of the liquid that fills the same volume as the object. If you then multiply that by G, we've now got the weight of the liquid, which is the same size as the object. So this difference here, this upthrust, that is the upthrust, the difference in the force, and that is equal to the weight of the liquid displaced by the object in the liquid, because we've got volume X times A multiplied by rho, which is the density of the liquid, so that's the mass of the liquid all in all, multiplied by acceleration due to gravity, so that's giving us the weight. So the upthrust is the weight of the liquid displaced, and that is our upwards force. Now this isn't always going to be enough to stop it from sinking. If the object is more dense than the liquid, then the weight is still going to be greater, because the rho here, we've got a battle of densities going on here. So the weight acting down of the object is going to be X times A times, so this is the rho of the object multiplied by G, and the upthrust is equal to X times A times the density of the liquid multiplied by G. So we've got the same X, A and G in both of these equations. So which one is going to be the dominant force depends entirely upon the density. So if the density of the liquid is greater, then the object will float. If the density of the object is greater, then the object will sink. So that covers everything really that's going on with buoyancy and upthrust. I suppose the only thing I haven't mentioned is this description of the upthrust is equal to the weight of liquid displaced. That is Archimedes' principle. Oh, I've written it here. I didn't even notice on my last bullet point. So Archimedes' principle, that's what this is referred to, this finding that the upthrust is equal to the weight of the liquid displaced. That is Archimedes' principle. That is Archimedes sitting in his bath and then shouting Eureka and running out into the street without so much as a towel. So, quite exciting to the certain people at certain times when they discover these sort of things. Obviously an excitable chap. But yeah, that's why it's named after him, because it was Archimedes who supposedly first discovered this. So yeah, there you go. That's a quick run through of drag and terminal velocity and buoyancy and upthrust.